following on from the previous video, we got to this stage here where we're given the whole family of these graphs here. If you want to find the equation of a new function in such a way that is always perpendicular to all the members of this family here, then you have to look at the gradient at this point here, say, is given by this. But then if you want to create something that's perpendicular to that, then you would need to take the negative reciprocal of that. So it will give you this. So we got to this stage here in the previous video. So from here, so we got to this stage here. That will then take us to this. So from here, get all the y's and all the x's on one side, and then integrate. So from here, separate all the variables. That will then take you to this stage here, okay? And then integrate. Well, find the antiderivatives. So from here, that will then take you to here. And then one of the theorems allows you to rather than trying to integrate this here, one of the theorems allows you to take the minus out here. So that will then take you to here, and then now integrate equally to both sides. That will then give you this, okay? And then rearrange this. That will then give you this. And when you get to this stage here, remember this equation here, plus x squared equals r squared. Well, this is an equation for a circle. Okay, well, this here, because there's a slight variation here, this here is actually an ellipse. Okay, so if you get a graph plotter and plot, well, stick any number into here. So like a 2 or a 4. Stick a number into here. You will get this. So you see the equation of this thing here, the ellipse here, is given by this thing here. Okay, so if you look at this here, it's always perpendicular to all the members of the family of the y equals a x squared family. Okay, so if you look at this here is 90 degrees. Okay, this here is 90 degrees. This is a 90 degrees. This is 90 degrees, and blah blah blah. 90 degrees here, 90 degrees here, and so on. So here we've created an equation for a case where it's always perpendicular to all the members of the y equals a x squared family. Okay, something to note. Hang on. Going back to here. Bear with me. Looking at this here, if you differentiate this, that will then give you dy by dx equals 2ax. Okay, so we've got one way of finding the gradient of at a particular point. We also have this way of finding out the gradient at a particular point. So in the example we use this one. We could alternatively use this one here. Well, if you want to create a new function in such a way that it's always perpendicular, you could also use this. Well, remember that to create something that's perpendicular, you need to take the reciprocal and then stick a minus in front of it. So earlier we used this one. We could alternatively use this. So now our new function, the derivative of our new function, must satisfy this. Take the negative reciprocal. So take the reciprocal first. That will then give us this, and then stick a minus in front of it, and then yeah. So we could alternatively use this, and then you would then separate all the y's on one side, all the x's on one side, and then integrate it, and blah blah blah. And it turns out that a log is involved, and when you draw a log graph, this here is always 90 degrees and 90 degrees here, and so on here. You could, the point that I'm trying to make here is that when given this here, if you differentiate it, you're going to get y equals 2ax here. Sorry, dy here. Hang on. You're going to get this, dy by dx equals this. So we could use this, or we could use this. If you use this here, you get a a whole family of ellipse. If you use this one here, you're going to get a whole family of logs. Well, try it for yourself. Okay.